isomers. So we'll start with our organic unit first. You and your buddies can pick the appropriate number of carbons. Did you ask? Who asked for isomers? Yeah, pick a number from like anywhere between 4 and 8. 7. So C7H16. The H comes because you double this and add 2. So we could draw all the structural isomers for this. Let's give that a try. The way I do it is draw the longest chain first. 2, 4, 6, 7. So there's the longest uninterrupted chain. And then I make it one shorter. This will kind of fit well with conformers, actually. So here's 6, and I have one branch, a methyl, to stick on here. So for example, I could put it here. Anywhere else that I could put that's different, I put it on the second carbon. Third, okay. Is that different, yes or no? Yes, yeah. This would be 2-methyl hexane, and this would be 3-methyl hexane. Is there anywhere else I could put it on a 6 that would be different? You don't think so? Okay, that's fine. Let's do 5 now. So go one shorter. 5. Now have 2 things to stick on. So for example, I'll stick them here. Is there any, so that would be 2,2-dimethyl pentane. Is there anywhere else I could put them that would be different? Yeah? You want it here. Okay, that would be 2,3-dimethyl pentane. Is that different or the same? Definitely different. Is there any other way I can do it? You want them in the middle? Yeah, that would be 3,3-dimethyl pentane. Anywhere else I could do this? Yeah. The 2 and the 4 position? Yeah, that would be different. 2, this would be 2,4-dimethyl pentane. Anywhere else? You're missing at least one. You want 2, like on the right-hand side? Okay. Oh, no, you take it back. Why would you take it back, or anyone? Yeah, we'd have to get rid of that one. You might know why? Same as this one. That's a conformer. So you see how it's the same. This is 2, this is 1, 2, 3, 4, 5, 6. So we made another 6 again. And that would be the same name. 2-methyl hexane. So don't draw that one. Okay? Anyone else? We're missing one. On which position? 2, 3, or 4? 3. We call that an ethyl. Yeah. So that's a 3-ethyl pentane. That would be different. All right, I think that's all of them for 3. Now we go down. My style is to go one shorter to 4. Now we got 4, but we got 3 things to deal with. So I'll do 1. We could do this. That would be 2,2,3 trimethylbutane. Anything else you see besides that one? It's sort of like a puzzle. You guys sit and think about it for a minute. Sure, let's do that. Second or third position. Okay. Is that cool? Why not? Yeah, you can't have 5 bonds, 2 carbons. No. Don't have 5 bonds on the second carbon, not possible. Anything else? Did I miss any? Okay, let's do that. How about that one? That's a conformer of which one that has already been drawn? Or it's in this list right here, this column. First, second, third, fourth, or fifth. Second, yeah, this is 2,3-dimethylpentane, and that's also 2,3-dimethylpentane. So these two are conformers. Nope. You've increased the chain length by doing this to 5. 1, 2, 3, 4, 5. And so you're back in this category again. So don't make the chain longer when you're doing it my style. Yeah, you want to go systematically. 7, 6, 5, 4, etc. All right. Is it possible to do this? I think that's the only 4 that I can think of at this moment. Is it possible to do this for a 3? You do 1, 2, you got 3, so you got 4 more to deal with. I guess you could do that. What happens when you do that? Yeah, I got 5 bonds. Yeah, it's just terrible all around. So I don't think it's, you could, yeah, I don't know how you could do it. You could cross that out. What if I cross that one out? This has 1, 2, 3, 4, 5, can't get to, I don't think I can get to 7. Yeah, I don't think it's possible. Once you get too short, it's not possible. There's too many things to stick on it. All right, so we got how many? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Cool. So that would be, yeah, a harder isomer question. I'll probably keep a harder one for the final. Do like a medium to easier one if there is one on exam 2. FYI. Okay? Is that good with isomers? So you gotta go systematically. The reason I'm saving harder ones for the final is there's more fun stuff you haven't learned yet. Yeah?
What about the cis and trans?
Those would be isomers. That doesn't apply here. But the question was about cis and trans. So if I drew something like this and I wanted an isomer, it wouldn't be a structural isomer, but a geometric isomer would be this one, like that. So the top one is trans, the bottom one is cis. So if you end up with something with a double bond, you might have a cis or trans. If I end up with this, what would be the, is this that cis or trans, first of all? Remember there's H's here. H. Cis or trans? Neither. Neither. You need two entities, like 2 entities here on the same side to be cis, or 2 entities on opposite sides to be trans. So this would be neither because you don't have 2 of something. Just like in transition metals, you need 2 of something, have cis and trans. The same idea here. Okay, is that okay? All right, next. Let's go on to, so we kind of did conformers. Conformers comes up a lot when you draw isomers. That's the main time in this class you would see them. You just want to say, if I redrew something, did I make the chain longer, or did I kind of put it in the same way as one of the ones up above? That's the main time you would see that. So you'd want to recognize a conformer as being identical to hopefully something you just drew. All right. Let's do functional groups. You'd want to be able to identify functional groups for anything I gave you. So let's try this. Okay, I'll give you a moment. Look for all the functional groups you can see here. Let me draw another one while you're messing around there. All right, I guess that's good. Okay, let's try the first one together. What functional group do you see for that first one? There's at least one. There's an ether right there. How did you know it wasn't an ester? Yeah, to be an ester, that would need to be a carbonyl, not that one. Okay, so what do you call this? Not a carboxylic acid. Aldehyde. Yeah, aldehyde has an H on one side and a carbon on the other. If it was a ketone, it'd be carbons on either side. Okay, what do you do with this? It's something. It's an alkene. An alkene. Okay? Has double bonds. So you call it alkene. Let's take a look at the one down here. Okay, what do you call that? As a carbonyl, it's one of your carbonyl derivatives. That's an ester. Yeah, you have an O right directly attached to the carbonyl. So we got an ester right here. Only one functional group, that's it. All right, over here to the right. You got an alcohol and this is an alkene, that would be called an alkyne with a Y. So an alcohol and an alkyne. All right. Cool. As identification, that's basically what the question would be about. Okay, let's see. We wanted some hybridization, and that was mostly related to the scheme and drawing. Is that right? More of the drawing? Okay. Kind of have to draw it out then, draw the electrons then. For sp3, if you're going to draw the hybridization scheme, it would look like this. There's 4 sp3 hybridized orbitals with 1 electron in each. Okay? To draw the simplest example of that for carbon would be CH4. It's the smallest one that would have sp3 hybridization. What would that look like? Well, it would be a carbon. It would be tetrahedral. How do I know it's tetrahedral? There's 4 groups on that carbon right there. So by the 4 groups, I know 2 things. Because there's 4 groups, one thing I know is tetrahedral. Second thing I know is sp3 hybridization. So from the groups, it tells you the shape and the hybridization. All right, so there's 4 groups. I'll try to draw this somewhat tetrahedral looking. These are 4 sp3 hybridized orbitals. All right, sp3 next to one of them, but all 4 are hybridized, sp3 hybridized. As the picture shows, they all have 1 electron. Okay? Now, these are bonding with 4 different hydrogens. Those hydrogens are all 1s1 from the periodic table, so they all have 1 electron. So we have an s orbital coming in for all 4 of these. These are all hydrogens. All the hydrogens are 1s orbitals, and they all have 1 electron. So I'll put 1 electron bonding with the other electron. That'll form a single bond with all 4. So that would what the orbitals will look like. All 4 of those bonds are what kind of bond? They're all sigmas. The bond happens between the center of the nuclei. So they're all sigmas. It takes 2 electrons to make a bond. You want me to draw another one for you? This? Okay. For hybridization, for the hybridized orbitals, they'll have 1 electron. If it's carbon, and we're doing carbon. And you just go from left to right. That's just convention instead of going from right to left. Yeah, if you're drawing sp2, the question is how the electrons fill. The bottom part is sp2. These are sp2. This is an unhybridized 2p orbital. This keeps its electron from before. So it carries over. And the other 3 now you fill in as normal. Yeah, so you want to go 1, 2, 3. I guess you could. It doesn't matter which order you really fill it in here. But the 2p has to keep its electron. So it'll look like that. Okay. All right, anything else on hybridization before moving on? So you'd want to identify, if I gave you a picture like this here that we were looking at before with the functional groups, all these carbons here, you should be able to identify the hybridization. Do you want to do that together, or are you cool? You want to do, let's do a couple. Okay, this one is that carbon right there. sp2. Yeah, remember that you got to count groups. It's all based on groups. So it's 1, 2, 3, 4. Well, 2, 3, and 4 really. This is sp. This is sp2 and sp3. So you have 3 groups here. It's sp2. This one right there. sp3, there's 4 groups, 2 undrawn hydrogens. Let's skip the oxygen for a moment. That one right there, sp3, there's 1 undrawn hydrogen. So if it gets you a little tripped up, you should draw the hydrogens in first. Yeah, everything has 4 bonds. This one will have 2. This one will have just 1. That'll have just 1. Just 1. Just 1. So if you get a little tripped up with the hydrogens, draw them in first. So this is that one right there. That one. sp3. All the others are sp2. The oxygen is sp. What did you say? sp3 because the lone pairs. You got to remember the lone pairs. So if you look at the periodic table for a second, carbon has 4 bonds, 0 lone pairs for formal charge 0. Move over 1. Nitrogen has 3 bonds, 1 lone pair. Move over 1. Oxygen has 2 bonds, 2 lone pairs. Move over 1. Fluorine has 1 bond, 3 lone pairs. Move over 1. Neon has 0 bonds and 4 lone pairs. So it follows that pattern. If that's something you forget, write it on your periodic table before starting the exam. So this one likewise, notice that both oxygens, 2 bonds, 2 lone pairs. This one has 2 bonds and 2 lone pairs. We often don't draw the lone pairs in for you.
If we're going to draw the lone structure of an organic structure, can we just
Yeah, you can do the bond line, and literally on the exam I write that. But you could do the expanded, I guess a condensed for the hydrogens if you wanted to. We could accept also. So let's do a Lewis structure if there's no more questions on this. Yeah. Oh yeah, you want to do that? That's fun. Which one? You asked, so you pick. This one? Okay. I'm going to give you about 10 seconds to count all the sigma and pi bonds here. I recommend starting with pi. Pi bonds? 2. From the 2, the triple bond. It'll have 2. One's a sigma and 2 are pi. Okay, anybody get the sigmas for me? It's only 6. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Like 13 or something. Did you draw on the hydrogens? I hope you did. Drawing all the hydrogens. There's 1 here. There's 2 here. There's 3 here. I think that's all of them. So let's count. You can follow my pen if you're a little confused on the counting. Sigmas, every bond counts. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and this one 13. I think it's 13. Yeah. Why is that there?
No, the one on the
Here? No, here.
the one on the right, like to the right of the triple bond.
Oh, there.
Yeah.
Well, that's a carbon right here. Why is there a hydrogen there? Every carbon has 4 bonds. 1, 2, 3, and 4. All right, so that's why there's a hydrogen there, because you need 4 bonds total. The other thing I would ask, sigma pi bonds, number of hydrogens, we kind of did that, number of carbons. Could ask for all the hybridization, and I could ask for the number of lone pairs on the molecule, which would be 2. 2 lone pairs. Okay, any other questions? All right, let's go on to Lewis then. We'll do Lewis, focus on organic here. I did hybridization scheme. This will be the last thing for organic. Oh, we're going well. Nice. Okay. So I could give you a molecule like something like that. So do you want me to draw it out the Chem 2 way or the Chem 2C way? I'm okay with either, or both. You want to see both? So if I'm doing the Chem 2A way, then I would say valence electrons equals a 1, 2, 3, 4 carbons in column 4 plus hydrogens, 1, 2, 3, 4, 5, 6, 7, 8. 8 hydrogens in column 1 plus 2 oxygens in column 6. Wow, what does that add up to? 24, 32? Okay, until you correct me, I'll say it's 32. So now let's draw the skeleton. C, and then there's a list of hydrogens. That means the hydrogens are around them. Then the next atom is a C. And then there's 2 hydrogens around it. And then the next atom is an O. And then the next atom is a C with 2 hydrogens around it. And then the next atom is a C with a hydrogen next to it and an oxygen next to it. Oh, 36? That's fine with me. Okay? So, now I count the skeleton. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So I've used 26 of the 36 electrons. 8, 10, 12, 26, yep. So now, normally in 2A I'd go to terminal atoms. All the hydrogens are used up, so hydrogens only have 1 bond. So I go to the oxygen. Let's see, it was 26, 28, 30, 32. All the carbons have an octet, pretty much, except for this weird one right there. But the oxygen definitely needs an octet. So 34, 36. That'll do it. That'll have all my electrons. Do I need to fix this at all?
Yes.
Which one? A carbon on the right. So I will scratch out one of these, erase it, and make it a double bond. Now is it okay? Okay, I'm done. So every carbon, every atom has a 0 formal charge. Every atom that needs to have it, it has an octet. If I was doing it the Chem 2C way, then I would go like this. Well, and if you don't like this style, that's fine. I start drawing the skeleton, CH. I'd get to the O, and I'm like, well, an O has to have 2 lone pairs, just like we talked about it. So I'm going to put the lone pairs there. Then I would have to the 2 H's again. And then CHO is a typical way to write an aldehyde. So I'll draw an aldehyde. Done.
Would that be considered delocalized
Does this have delocalized electrons? What do you think? So the real question is, does it have resonance structures? It could with a lone pair of electrons up there. To make the very first structure we drew before I erased it, it would be a reasonable Lewis structure, or resonance structure. So it could have a little bit up here on the upper right. Then I'd want you to draw the shape. So if I'd recommend just doing the bond line formula. Oh, well, let's do bond line first, and then talk about the shape. If you want to do bond line, super easy. Got 2 carbons, then an oxygen, and 2 carbons, and the second carbon is an aldehyde. So it looks like that. Okay, so you zigzag the carbons back and forth. If you want to draw the 3-dimensional structure, which I could ask for, actually by drawing the bond line, you've kind of done it. Because what shape is the well, let's say these 2 carbons are what shape? These 2 carbons right here. How many groups do they both have? 4. So that's tetrahedral. But because we're not drawing the hydrogens, you don't need to draw all the tetrahedral. So the carbons just look bent, even though the hydrogens on them would be tetrahedral. So we got those tetrahedral, that would be tetrahedral. This would be a tetrahedral bent structure, it's already bent. And this would be trigonal planar, because that carbon has 1, 2, 3 groups, and I've already drawn it trigonal planar. So I'm done. If you did it the really, that's why I'd recommend it doing it this way. You're not drawing all the tetrahedral craziness. If you did want to draw it, you'd have to draw it out. You have to draw all the dashes and wedges. So you'd be drawing, basically by adding the hydrogens, you're drawing the dashes and wedges. So you draw that if you wanted all the tetrahedral action. And 3 of the carbons are tetrahedral. But you don't have to include the hydrogens if you're doing bond line. Any questions on this? Yeah?
So, would it have mattered if you did like the Lewis one above, where you just put like, you did draw them then like that on the end of the O and H?
You mean this here?
Yeah. Like if you just draw the H coming up from the top of the C and then double bond straight across the, like, from the C.
If I put the H and the O in different places, that would be okay, and that's called what? Nope. What if I did, so, for example, if I drew the H right here. What's that called? Conformer. Because it's just moved around a little bit. But this is not showing shape. So we don't care where things are. It's just whatever. This is showing shape, and it could have some rotation. So there could be different conformers you could draw that would be correct. Yeah. Any other questions on Lewis? Oh, yeah. Yeah, if you don't want to draw the H, you don't have to, because if you're doing bond line, you could just do that. Totally fine.